In this video we're going to look at how to construct a peak model in CasaXPS. The peak models that we will create are for spectra that derive from this type of material. And this material has been chosen because we've got three different atoms, nitrogen, oxygen and carbon. They all have 1s photoemission lines, and we find nitrogen appears once in this material in a triple bond with carbon, so we would expect to see one peak for nitrogen 1s. For oxygen 1s, this has a double bond to carbon and single bonds to carbon, so we would expect to see twice as much oxygen as nitrogen, and these component peaks corresponding to the single bond and the double bond should be offset in binding energy. And then when we move to the carbon 1s, because we have 6 carbon atoms all in different chemical states, we should see at least 6 component peaks under the carbon 1s envelope that are all of equal size. The simplest spectrum from this material will be the nitrogen 1s. So we'll examine a nitrogen 1s spectrum that has been measured using Pass Energy 10, so this is a high energy resolution mode for this instrument, and we have data that includes, as we expected, a single spectral peak here, and what has been defined on these data are a background and a single component. And the idea is that we adjust the area of the peak, the full width half maximum of the peak and the position of the peak using an optimization algorithm, so that these parameters end up with a component peak located with respect to the data such as the residual standard deviation is a minimum. So the position, the full width half maximum and the area are fitting parameters, and these move within an interval. At least this is how the constraints for these parameters have been defined for this particular peak model. So we have an interval for the position, an interval for the full width half maximum, and similarly an interval for the area. And when we bring up the quantification parameters dialog window, we can see the background that is defined, and the component is defined in terms of parameters including a line shape. And when we say fit, the parameters are adjusted so that we end up with a fit of the component peak to the data itself. And you can see the residual standard deviation is less than unity, so this is fitting the data very well. And more importantly, the residual standard deviation looks uniform across the interval. And so on balance you would say that this component peak with this line shape and the background that has been defined for these data altogether model the data very well, and we would expect to be able to measure a position and the area based on this component peak when fitted to the data. The initial parameters that are used in an optimization are specified using text entry fields on the component's property page. So I could specify I wish to start my optimization using an area of 2000. I could also specify that I want the full width half maximum to be 2, and let's offset the energy to a new value. And so we end up with initial values that start the optimization process, and these values will move within the range of the parameters as specified in the area constraints, the full width half maximum constraints and the position constraints. So I could adjust this one to say 3, and you can see the full width half maximum constraint has been updated, so it now moves in an interval from 0.22 to 3. Not that it influences this optimization at all, because the parameter, when I press fit, it ends up with a value of about unity, so it's well within the range that's specified here. So the text entry fields allow you to specify specific values, but you can also use the cursor and point at these various points on the component peak, and then this will update the position and the area according to the movement that was made. And then you can go to the side of the peak and make an adjustment, and you can see the full width half maximum adjusts and the height adjusts to maintain the same area. If you wish to keep the same height, if you hold the shift key down, you then adjust the forward half maximum, sliding left and right, you can end up with a new forward half maximum but a different area maintaining the same height. So again, if we wanted to fit that, we just press fit and it'll find the best fit for the parameters based on those new initial conditions and the optimization steps that lead to the best residual standard deviation. A single peak is the simplest case for optimization. The next peak that's worth looking at in these data are associated with the oxygen, because we've got oxygen single bonded to carbon and then we've got oxygen double bonded to carbon. So if we now look at the oxygen peaks, we see that there are two peaks, and this gives us the opportunity to start from the beginning and go through and create a background which then approximates the signal that corresponds to scattered electrons, inelastically scattered electrons, that result in a loss of energy from photoemission peaks with higher energy. So this is not the signal that is relating to the amount of oxygen, it's only the signal above this background that we're interested in calculating for quantification by XPS. And once we've got a background set up, we can then apply a pair of peaks. I'll just turn off the fill option and then I will adjust this peak and add another peak. These two peaks must correspond to the two different bond states for oxygen, and when we say fit, we obtain an approximation to the positions for these in terms of binding energy, and these will be characteristic of these different bond states, and the relative intensity of these peaks, well, they should be 1 to 1. So this is approximately 1 to 1, and as it stands, these peaks have been fitted using 6 optimization parameters: area, forward half maximum and position, and there are 2 of them, therefore there are 6 parameters. So if we adjust these in any way and then say fit, we return to the optimization state that appears to be best for these data. We can also introduce constraints when we've got a pair of peaks so that we produce fewer fitting parameters. So for example, we might believe that these peaks are related in terms of area, and if I force these to have the same area, so the peak in column B is related to the peak in column A through the area constraint by constraints of the form A star 1. And similarly, I could say I want to form a constraint between the position of A and the position in B. So in other words, the position of the component in column A is calculated to be an offset, which is specified, from the position of the peak in column B. Now I'll remove that, and I can do that by saying #2, and that will cause an interval to be created about the current value plus or minus 2, so that gives me some movement of this peak. So when I do the optimization, I've now got 2 peaks that must have the same area, and the test is, do they fit these data and also produce this ratio of 1 to 1? And the answer seems it's reasonable. It's not as good a fit as we had before, but nevertheless it's a reasonable fit, and we can try and adjust this by altering the line shapes. So I've changed the line shape, made it less Gaussian, and I've said fit again, and this has produced a fit with a better residual. I can also point at the end and give an offset to the region, and that allows me to just try and adjust the background manually so that I get a better fit here. And having adjusted the background, where the background ties to the data under mouse control, and then saying fit, I've ended up with a similar sort of residual with these 2 peaks, the same quality of fit, looks like a uniform residual standard deviation, and a value that was about the same as for the nitrogen. So from this, although I can't deduce that I have the same area ratio based on optimization, I've imposed that, so this is my interpretation of these data. But what I can say is that if this is true, then the component peaks will have positions of these two parameters. So let's see how to display those parameters. So I'm bringing up the annotation dialog window, the components property page, and I can include a few of these items now. And I'll exclude the constraints so that we can just see now a report that is based on these two peaks that have been fitted to these data. The next level of complexity for these samples is in the carbon 1s, and that's because of all of these possible bond states. So when we look at the carbon 1s spectrum, well, you can see that the peak is actually a structure that could easily be 6 components or possibly more. And the question of how to look at such a data envelope using constraints deserves a video all to itself. So we'll consider the carbon 1s spectrum in the next video.